Okay, in this video we're going to get the units all straightened out, the abbreviations, and then also look at Ohm's law. So let's start with something we're familiar with here, like temperature. We could abbreviate with a T, and then the actual units we would use would be degrees. And that's abbreviated, with a little circle right here. So temperature T measured in degrees, little circle. For electricity, we have things like voltage, that's abbreviated V, measured in, so voltage V measured in volts, also abbreviated V. Current is abbreviated with an I, not a C. The units, it's measured in amperes or amps, right? And that is abbreviated with an A. Then there's resistance, abbreviated with R, and it's measured in ohms. Ohms, the symbol for ohms is sort of like this little horseshoe type thing. I can draw it again if you want to try to see it, something like that. Conductance, if you remember, it's the inverse of resistance. It's just the opposite. Glass half empty, glass half full type thing. So conductance is abbreviated with a G. Again, not C. So current is abbreviated I, conductance is abbreviated G. Probably when you get down here to charge, well, let's see, C was taken for coulombs way over here at the bottom. So, okay, back to conductance. It's abbreviated with G, and it's measured in, you have two choices here. It is the inverse of ohms. So you can just use mhos as your units. 1 mho instead of 1 ohm, would be the inverse of 1 ohm. And being the inverse of ohms, you can use the abbreviation of just an upside down sort of horseshoe symbol like we have right here. Alternatively, you can use the units Siemens and use just an S to represent conductance for the units of conductance. Finally, we have charge, abbreviated as Q, and it's measured in coulombs, and that's abbreviated with a C. Okay, so you want to have those down pat. I mean, just memorize, because we won't be writing all the words out. We'll just be using the letters. If you remember from a previous video, voltage is really our imbalance that wants to equalize. It's an imbalance of charge. Something I didn't mention, but it's a key point, is that voltage is the difference between 2 points. So later on, we'll try to get that across, and you'll hear me sort of always stressing the fact that you can't say that you have voltage at a point, like here's the voltage at this point. There's always an unspoken reference. If you're not mentioning the other point, that would be the reference point. But it's good to get in the habit to always be thinking of voltage as 2 points. It is. It's the difference between 2 points. And in our water analogy, we had sort of 2 different points. There's a water level there and a water level there. And the difference there is our sort of our voltage, if it would be a difference in charge. And then if you remember, we can provide a path, and the path that we provide has properties of how easy or difficult is that path to get through, and that would be conductance is how easy, resistance how difficult. And then there's the flow, the current. So I mean here, this path, let's jot that down. That would have a certain amount of resistance, or conductance. We could understand it in those terms. And given a certain amount of voltage and a path with a certain amount of resistance or a certain amount of conductance, you will get a certain amount of flow, right, from high concentration to low concentration. And that flow is the current, abbreviated as I. So there you go. So there we're using our letter abbreviations for voltage and the path, resistance or conductance, and then the current here. It flows. Okay. Once we have these units defined, it's easy to explore what Ohm's law is all about. And it's a very simple relationship. You can draw water analogies and talk about, how increasing, pressure, which is really comes from that imbalance that wants to equalize. You can talk about the relationships between pressure, resistance, and flow, and those are standard fluid dynamics, no matter what is flowing, actually, whether it's electrons in our case, or positive charge also going the other way, or other things like water, or you name it. But those are always, or air flow and so on. Those fluid dynamics are always the same. But let's look at Ohm's law and use our newly defined abbreviations and really map it out as what is the relationship between voltage, current, and resistance. So let's go ahead and do that. So Ohm's law, don't make it hard. It isn't. So we can map it out mathematically. Given a certain amount of voltage, V, and a path with a certain amount of resistance, you will get this much current. It's simple. So we can just use mathematical relationships to capture the relationship between these items, to capture the relationship of these fluid dynamics. It's very easy to spell it out with math. And I mean, just these basic relationships right here, this would be Ohm's law. You can, of course, rearrange it algebraically, and all the different forms are true. I mean, here I kind of mapped it out by saying, given a certain voltage V and a path with resistance, I'll get a certain amount of current. But other things are true also. Like, let's look at it this way. How about shuffling things around algebraically? Given a current that's flowing through a path with that much resistance, through a current flowing through that much resistance, it will develop a pressure across that resistance that's equal to a certain voltage. Or you could go backwards with this formula and say, you might be wondering how much voltage is required to push a certain amount of current through a known resistance. So you would just take the current that you want times the resistance of the path, and you'll know what voltage you would need. I mean, other forms, right? We can just keep pushing things around. We could say, if I have a certain voltage and I have a certain current flowing, what is the resistance of the path? So I can define the resistance of the path easily. If I know the voltage that's being applied and I know the current that's flowing, I can measure those things. Then I know the resistance of the path. And if I wanted to know the conductance of the path, I just invert the resistance. So I could take my conductance as my thing that I'm trying to find, and it would just be 1 over R. So I can just talk in terms of the conductance of the path easily. The inverse key on your calculator will be very handy for those back and forths between resistance and conductance. And the way Ohm's law works is simple, of course, and then it let's just see, let's explore. We had said, I think, in a previous video, you could double the voltage, and we would expect the current to double then because you've got twice as much pressure. And you can see Ohm's law is going to hold that truth also. I mean, the math is just easier than drawing water analogies, right? So if I were to double the voltage and the resistance stayed the same, then I would get twice as much current, right? Yeah. And I think we also mentioned in the previous video, just by way of example, let's say I doubled the voltage, but I also doubled the resistance. Okay, current remains unchanged. It remains what it was. What if let's not do that. Let's double the resistance, but keep voltage the same. So let's say I had voltage, and but I doubled the resistance. Current, think of this as a 1 here. That's just 1 unit of volts. Current will be right in half, right? Okay. So that's Ohm's law. Very basic, very important, and easy to use, but don't forget about it, and always believe in it. What other examples could we do here? I mean, you could use that. That was just using this this first arrangement, but I think you get the idea. Just pushing Ohm's law, rearranging it. I don't care how you memorize Ohm's law. It's sort of a cause and effect thing. This one's kind of cause and effect. Given a certain voltage and a path with a certain resistance, you'll get a certain current. This is also cause and effect, though, in some ways. If you have a constant current source and you push current through a resistance, you'll get a certain voltage. IR drops, we know this as IR drops. We'll get to know that. I don't know that I'm big on memorizing every form. I mean, they'll get in your head and you'll know it. But I mean, some people try to memorize equations, and what that means is you've got 3 equations to memorize. I'm sort of more interested in you understanding the relationship, and you just pick one, and then of course you've got algebra to push things around for you. You don't want to approach your study of electronics just by memorizing. That's not going to work out. There's too many things to memorize. So there's probably thousands of things to memorize or more, and but you'll find that there's not that many things to truly understand. So if you truly shoot for understanding, not memorization, that's the key, and we'll be talking about that a lot. I'm thinking of other examples before we wrap this up. Some extreme cases, Ohm's law will show you, I think, the light. Let me jump back to a water analogy, and let's just say I had the imbalance here, but I have no path. No path is really, zero conductance or infinite resistance. So that's an extreme case. Let's see what Ohm's law tells us about that. Back up to this formula here. If we have infinite resistance, the denominator here will be, infinitely large, and current will be infinitely small. So in a sense, Ohm's law it'll tell you, zero current. And that makes sense, right? I mean, intuitively, you just look at this and there's no way for any current to flow. There's no path. So, yeah. In fact, what is Ohm's law showing us? To get current, you need 2 things, right? You need voltage and you need a path. Well, like for example, Ohm's law also would hold true here. If we had the same water, maybe we have a path, but we have no voltage, right? How much current will you have if there is no imbalance? So let's look at that. We can go back up here again to this one, first one. So if resistance is anything, I don't care what resistance is, right? let's say resistance is 10 ohms. But if voltage is 0, right, current will be 0. So there again, Ohm's law just keeps you from having to draw these little analogies for yourself. You just trust Ohm's law. So if you have no imbalance, you will have no current. There's no demand for flow, no pressure to make the flow happen. So so that's this extreme case. 0 volts, I don't care what your path is, there won't be any current. Or so if you have voltage and no path, no current. If you have a path but no voltage, no current, and so on. So you can just play with those things. You can use the analogies, experiment with the algebra, pushing Ohm's law into different arrangements, and really get comfortable with what Ohm's law is telling you. That's a big deal. Here's a good one. Try to wrap this video up. I don't want it to be too long again, but here's an extreme. How about, let me do it this way. This is sort of my 2 tanks, but I wanted to try to represent 0 resistance. And my question for you is, can you have voltage if you have 0 resistance between the 2 points? And the answer is no. There's no way to establish a difference between 2 points if there's 0 ohms between them. And that's known as a dead short. You can't, right? I mean, try to establish a difference in water level, if we were using the water tank analogy, when they're connected essentially by 0 ohms. You cannot establish a water level difference if you have 0 ohms between the 2 points. And so that's, again, these are so important, and I'll try to maybe keep referring back to some of these extreme situations. This one, just quickly, I'll finish this video with a little example of why I'm so emphatic on these things that seem so simple. I mean, this saved me a whole weekend of work here. I was working with a physicist. There's an evaporator that can pretty much melt and vaporize anything, any known substance. So it's pretty cool. It shoots an electron beam, very mad scientist type stuff. It's got this big bell jar that comes down, pulls a vacuum in the chamber, and then it fires in this electron beam into this little ceramic crucible. Whatever's in that crucible is toast. I mean, it can absolutely melt anything. It can melt rocks if you put rocks in there. So it fires in an electron beam that's guided with magnetic fields and focused right on that crucible. So anyway, we had got this thing running, and I knew the system pretty well as far as that side of it. I hadn't ever had to do any repairs on the power supply, and so I hadn't learned that, and that would take some time. That was not something that I had learned yet. So anyway, but I got a phone call on Friday night, and they wanted to run some of this, and they said, hey, we're not getting any voltage from the power supply, so could you come in and have a look? And I thought to myself, oh, okay, because I was kind of in that kind of relationship with him. I was kind of on call, so I didn't. There goes my weekend, in other words, because I know this is not going to be short, and I'm not even sure I can learn this. This power supply is massive. I mean, it's on wheels. It's a couple 100 pounds. It's high voltage, high current. It's a little bit dangerous to be poking around in there too. So I was not looking forward to any of this. And there's a big learning curve, and I'm not even sure I can get that learning curve accomplished in a timely fashion, et cetera, et cetera. So as I'm driving in, I'm thinking, oh, this is going to be tough. I'm not so sure I can even promise much here as far as, how fast I could really get this thing solved. But then, as I'm sitting at a traffic light, I'm remembering Ohm's law, and I'm thinking, what would be the reasons they might not get voltage? And it occurred to me that maybe I'll have a weekend after all if something as simple, they were evaporating aluminum. And I thought, if some of that aluminum splashed out of the crucible, came down around to the electron gun, and shorted it out, that would achieve a situation where there's 0 volts coming from the power supply, but not because it's the power supply's fault. that 500-pound monstrosity on wheels that I would have to crack open the massive book on and try to learn what am I looking at as far as trying to fix it. I might have saved myself a month of work just from Ohm's law. So I thought, yeah, if aluminum had splashed and shorted out the output of that power supply, which is the electron gun, the power supply would, of course, have 0 volts, just because of this reason right here. This is what I'm looking at. So the output of the power supply has been dead shorted by a little splash of aluminum, if I'm lucky, and all I have to do is flick that little bit of aluminum off, and everything's restored. And I did remember too that the power supply is protected from dead shorts. It has a current limiting feature, so I had read that about it. So I thought it's not that it won't be damaged. It'll have been spared, but so again, so that little bit of putting both feet firmly on Ohm's law and thinking what could be the causes of 0 volts, because of course the team that I was working with, their first thought is, we're not getting any voltage. The power supply's dead, or something went wrong with the power supply because we're not getting any voltage, and that was just simple Ohm's law thinking to say it might not be the power supply. Anyhow, so I arrived there, put my ohm meter right across the gun where the crucible is, and saw 0 ohms, and flick that little bit of aluminum off. Quick fix, and saved my weekend. Okay, long story. I don't know if I could have told that a little shorter. So anyway, I hope you really understand and believe the importance of getting your brain to really embrace Ohm's law and really believe it. All right, we'll end this video here, and then we'll do some more other topics with some other videos.